In this video, we're going to look at some of the basic principles of what we call proton NMR. Now, we know that the nucleus of a hydrogen atom consists of only a proton. There are no neutrons in the nucleus, and NMR is a technique that looks at the nucleus. So often, hydrogen NMR is just called proton NMR because all that there's in the nucleus is one proton. So just to bear in mind that term proton NMR and hydrogen NMR, they're interchangeable terms. So we're going to do something very similar to our carbon NMR. We're going to this time be looking at how many different types of hydrogen there are in the molecule rather than how many different types of carbon. So we're looking at the number of peaks being the number of different types of hydrogen. And we're going to look at where they're located. And again, our data sheet's going to help us with that. You'll notice that the values for proton NMR are much smaller. They go from sort of 0 to 12 rather than from 0 to 250 on this parts per million scale. They're in a smaller part of the spectrum. The spectrum will be blown up so that 0 to 12 fills the sides of the page so that you can easily interpret it. So we're going to look at how many there are, the number of peaks, where they are, the type, using the data sheet to help us. So that's exactly the same as carbon NMR. We've then got two extra little strategies that we can use in proton NMR. We can look at the integration. Now, those of you who've studied some maths, maybe at A-level, will know that integration is the area under the curve. So the integration is going to tell us how big a peak is being produced, so the size of the peak, and that is actually going to tell us how many protons are in that environment. So if that peak is twice as big as a different peak on the spectrum, it's got twice as many hydrogens living in that environment than the other peak does. And then finally, there's something called the peak splitting. That's going to tell you not about the protons producing the peak, but how many protons are next door adjacent to the protons producing the peak. We will take that in a separate video because that's a really important technique that's really going to help you determine structure. So in this video, we're going to look at number of peaks, where they are, and then integration. So we'll just start with, similar to carbon, the number of peaks and where they are. We're just looking at what we get given on the data sheet here. And if I just draw a little example, we can work with it. So if we take something fairly straightforward like propane. So a nice easy structure that we know. It's got 3 carbons. It's got hydrogens. So remember, we're now not concentrating on the carbons, we're concentrating on the hydrogens. Now, propane is symmetrical about the midpoint, and so the hydrogens here, they're all the same as each other. If you imagine making a molly-mod model of that, you could spin that carbon round and those 3 hydrogens would all be identical, but they're also the same as the 3 at the other side because the molecule's symmetrical. And then the 2 in the middle are different. So we would expect, we've got 2 different colours of highlight in here, we'd expect to see 2 peaks. And where would we expect to see them? So they're all of a type where carbons are just attached to other carbons. And so one of these 3, I think the data sheet's a little bit overcomplicated here. If you just think of any hydrogen on a plain carbon chain as coming anywhere in this region of between like 0.7 to 1.6, then you're going to be okay. So all of these, our yellows and in fact our pinks in this particular example are the same type. So we would see 2 peaks in this region between 0.7 and 1.6. When we're thinking about these, remember that these are just ranges and we can be inside and outside of the range slightly. So we're just looking around about that region, 2 peaks. If we draw a different structure, so if we change our propane to propanone, if we have a look at propanone, what we see in propanone is, again, it's symmetrical, but there are no hydrogens on that central carbon now, so there's actually only 1 type of hydrogen, and it's now not just a plain chain because these hydrogens live next door to a C double bond O. So there's got to look down, but we can find it here. Yeah, they're living next door to a C double bond O, so we would see one peak on the spectrum, and it would be in the region delta 2.1 to 2.6. If I were to pick the isomer of propanone that's propanal, like this, we can have a completely different spectra. So we could use this technique to distinguish, whereas infrared wouldn't tell us anything about the difference between these two because they've both got the carbonyl carbon. But the hydrogen here in propanal is going to be different to the two that live next door to the carbonyl, which will be different to the three that live downfield, down the chain from the carbonyl group. And if we were to look at the types we've got, those red ones at the end would just be this 0.7 to 1.2 kind, but the orange ones would be the type that we'd just had there, next door to a C double bond O, and our yellow one, our aldehyde one, would be between 9 and 10. So we would end up with 3 peaks for propanal, 1 peak for propanone, and in very different locations. So the type and the position we can use our understanding of symmetry and our datasheet to help us with. And then we've got this new term, integration. So we're going to have a look at that separately. So the integration is the relative area, and it tells you about the number of protons in that particular environment. You often the computer is just going to print onto your spectrum the area under these peaks relative to the smallest peak. So the computer would measure the smallest peak and then see how many times bigger the area under the larger peaks are in comparison to the smallest peak. They could also do this as an integration trace, which is what is being done here. So they've measured the areas under the peak and represented that as what's called an integration trace, and that the height of that integration trace is going to determine the relative proportions. So what you would need to do is get a ruler out. Using your ruler, you want to be able to measure the vertical distance between these two lines. So if you sort of extend these two lines and then measure vertically, do the same here. Use a ruler and measure it vertically. If you do that, then I think you find that doing that one on your pack, if you've got this A4, you find that these are 7mm and 21mm. So you can see that comparative to the smallest, what the computer would do with that information is it would say that one is relative. If that's a 1, the smallest is a 1, this one is 3 times bigger. So they're saying that in this spectrum, 21 to 7 is equivalent to 3 to 1. Does that make sense for a spectrum of methanol? So let's just have a little structure of methanol drawn out. Meth meaning 1 with an OH. Why would there be 2 peaks for a start? Well, if we look, there would be 2 peaks because there's one hydrogen of this type attached to the alcohol group, and then 3 hydrogens of the methyl type. And so we've got 3 of one type and 1 of the other. And we can immediately tell that this is our 1 and this is our 3 straight away from our spectra. So we're just going to practice that a little bit. Let's draw some structures out. Propan 1 all. So we're going to go prop 1, 2, 3. AN, single bonds. On number 1, put an OH. Then make sure that every carbon's got 4 bonds. And then let's have a look at what we think we've got. How many different peaks do we think we've got? Well, we've got the H of the alcohol group. That is a unique one, different to everybody else. Nobody else is on an alcohol. These 2 hydrogens here are attached to the same carbon as the alcohol group. If we were to look on our data sheet, we could see that they would be in the 3.1 to 3.9 region because they're living next door to the O of an alcohol. Then we've got the 2 that live just 1 house further away, but they're not the same as the ones right by the alcohol. And then we've got the 3 identical to each other but different to everybody else that live on the methyl group at the end. And so in total we've got 4 different peaks. And then what we need to look is how many of each type of hydrogen have we got. So of the blue type, we've coloured in that there was 3 of that type. Then we had 2 of the orange type, 2 of the yellow type, and 1 of the green type. So if I just go over that, you can see that we did have 3 coloured in that type, 2 coloured in this type, 2 coloured in this type, and 1 in that type. So 4 peaks, and their integration would be 3 to 2 to 2 to 1. It may be that if we had an integration trace, that would be coming out as 6442, or it could be coming out as 0.3, 0.2, 0.2, 0.1, but the simplest ratio of that is 3 to 2 to 2 to 1. Let's have a look at bute. So bute being 4, an, single bonds, al, aldehyde, and make sure every carbon has their hydrogens. How many different types of hydrogen have we got? So on this spectrum we've got the aldehyde one. We've then got the ones next door to the aldehyde. We've got the ones next door to that. And we've got the ones at the end. So again, we've got 4 types. We've got 3 of the purple type, 2 of the red type, 2 of the yellow type, and 1 of the orange type. These 2 spectra then we may think, well, these are going to be identical. We're not going to be able to tell them apart. But we are going to be able to tell them apart because they've got different types of carbon. An alcohol carbon is very different to an aldehyde carbon. And so we're going to be able to tell the hydrogens on those carbons apart from their locations on the spectra. So their parts per million values. Pent, 1, 2, 3, 4, 5. AN, single bonds. Ketone on number 3. Everybody else just gets hydrogens till every carbon has 4 sticks. How many types have we got here? So we've got the hydrogens that are on the end, but if we look, this is symmetrical about the ketone group, so the hydrogens on the other end are exactly the same. Then we've got the 2 here being identical to these 2, and that's all our hydrogens. So we're actually only going to have 2 peaks here. And if we have a look then, how many are in each location? Well, we've actually got 6 of the yellow type and 4 of the orange type. Now, the computer wouldn't be able to do that because it does things in the simplest whole number ratio. So actually, the integration would say 3 to 2. We would have to work out that it was... that colour's the wrong colour, sorry. We would have to work out that it was 6 to 4 with some other information. I'm going to look at that later on. So the final factor is this thing called peak splitting. I'm going to take that in a separate video because it takes a little bit of explaining. So far we've said similar to our other type of NMR, we're going to have how many different types of hydrogen are there, where are they, and how big will each peak be, and that size is going to represent how many hydrogens are of that type.